Swayam Prabha. Digital India. Educated India.
With this lecture, I am going to start discussions on gyroscopic motions. Now, gyroscopic motions are observed in axisymmetric bodies rotating about its axis of symmetry about a fixed point in inertial space. So, that is gyroscopic motion. Therefore, we will first calculate the gyroscopic forces in spinning axisymmetric bodies and look at precession of precessional motions of these bodies with and without external moment. As I mentioned that we are discussing about motion of axisymmetric bodies spinning about the axis of symmetry and held at a point in inertial space, and this point is on the axis of symmetry. This is our prototype problem that we have been discussing. We have discussed in the past lectures. We have looked at these kinds of motion: precession, nutation and spin, and gyroscopic motion is a common phenomenon or a motion that is exhibited by tops, for example, and many other axisymmetric bodies. We will look at these examples. The first and foremost requirement is the spin of the axisymmetric bodies about its axis of symmetry, and it is fixed at a point on the axis of symmetry, and this is the origin of our inertial frame. But we use a frame which is not the inertial frame, which is defined in such a way that in this frame the moment of inertia tensor of this body is fixed, even though this is not a body fixed frame. This x y z frame, even though it is not a body fixed frame, yet because of the symmetry of the body, the moment of inertia tensor is constant in this frame. And how do we define this frame? The x axis is taken as a cross product of the inertial z axis and the axis of symmetry about which we have the spin. Therefore, this x axis unit vector is inertial z axis cross the axis of symmetry. This we have discussed in one of our previous lectures, how to fix up this frame in which the moment of inertia tensor is fixed, even though this is not a body fixed frame. Okay, and y axis completes the right handed coordinate system. Of course, z axis is the axis of symmetry. In this frame, an observer in this frame will always see the body aligned with the z axis, the axis of symmetry always along the z axis, because z axis is defined that way. It is the axis of symmetry, and therefore, even though this is spinning and this body being axisymmetric, therefore, the moment of inertia tensor in this x y z frame is constant. The frame angular velocity, this we have discussed previously. We are going to now write it explicitly in terms of the precession and nutation. The frame will be rotating because of precessional motion and nutational motion. Precessional motion is about the inertial z axis, but this I can always represent in my x and x y z frame because it is in the plane of y z, it is in the y z plane. That is the precessional angular velocity, and this is the nutational angular velocity about x axis. So, that is the angular velocity of the frame. Spin angular velocity of the body is p k cap. Therefore, the net angular velocity of the body is the angular velocity of the frame plus angular velocity of the body with respect to the frame. And here I have marked out what are the various terms. We have nutation, which is the rotation about the x axis, which is perpendicular to the axis of symmetry and the inertial z axis. And note that this x axis is always in the inertial x y frame, because it is perpendicular to the inertial z axis. Therefore, it has to lie always in the inertial x y plane. The second term is born out of precession, and the third term has contributions from precession and spin. So, this is our net angular velocity of the body. Now, moment of inertia tensor, as I mentioned, in this frame x y z, the moment of inertia tensor is constant. The moment of inertia about the axis of symmetry is I, which is I z z actually, and because of symmetry I x x and I y y are the same, and that is denoted by I naught, and these are fixed quantities, constant in this frame. Therefore, the angular momentum, defining angular momentum is straightforward. This is the expression of angular momentum. You multiply the moment of inertia tensor with the angular velocity, and this is your angular momentum about the point O. This is a fixed point in inertial space. So, this is our angular momentum. Now, we will look at the equation of angular momentum or the rotational dynamics equation about this point O, which is a fixed point in inertial space. The rate of change of angular momentum about O is equal to the net moment of all forces about O, or there can be couple moments as well. So, all moments, sum of all moments. Now, as per our prescription of total time derivative is the local derivative del del t of h naught plus frame angular velocity cross h naught. So, the second term on the left hand side is the because of the frame derivative. I plug in, I now start derivating the angular momentum about O, the local derivative. Now, I do not consider that this theta dot, psi dot, theta etcetera, these are constants. They can be in general changing. We are first trying to determine the general equations of motion, then we will look at some special cases. So, for general equation of motion, I must derivate, I must consider that theta is changing, theta dot can be changing, psi dot can be changing, etcetera. But what I do not consider to be changing is the spin. This is just an assumption, but you can always include the change in spin. So, what I do is I assume that the spin is constant and the net moment is only about the x axis. Typically for a top, for example, a top, it is the weight that produces the moment about point O. Therefore, suppose this is the center of mass, we will have the weight, and that is going to produce a moment about the x axis. So, moment is assumed to be only in the I cap direction. So, let us proceed with these assumptions. What I have done is I have written the final expression. Now, this is a straightforward algebra which you can do. You must derivate each and every term considering what are the variable things. For example, the first term in the temporal derivative, let me just write down this temporal derivative. this term is I naught theta double dot I cap plus I naught psi double dot sin theta j cap plus there will be another term I naught psi dot theta dot cos theta j cap plus I psi double dot cos theta minus psi dot theta dot sin theta plus p k cap. Then let me check whether I have got all terms. This is the first term, this is this term. So, these I have this and I have this and this. Oh, this derivated and this goes to 0, of course, this will not exist. P has been considered to be constant, therefore, that derivative goes to 0. That is the temporal derivative and rest of it comes from the frame derivative. Finally, if you look at the components of the equation of motion, then we have these three equations. I have, as I have mentioned before, we are considering moment only about the x axis. Therefore, the first equation has a non-zero moment, can have a possible non-zero moment. Now, these equations are highly nonlinear and coupled. They are extremely difficult to solve analytically or almost impossible to solve. You have to do numerical solutions for this, but what we are going to do is we are going to look at some special cases. The first special case is that of a steady precession. What do we mean by steady precession? It is something that we normally see for tops usually, but not always, that this angle theta, is constant. This angle theta is constant, which means theta dot is 0. There is no angular velocity. So, there is no nutational angular velocity. The other thing that we assume is psi dot is constant. This is constant. That means it is having steady precession about the inertial z axis, which is vertical. That is called steady precession. Therefore, it does not have nutational angular velocity and there is a steady precession, psi dot is constant. If you make these simplifications, then what we have is because theta dot is constant, so theta double dot goes off, other terms remain in the first equation, the other two equations completely disappear, they are trivially satisfied, because psi double dot is 0 and theta dot is 0, etc. So, the other two equations you will note they will be trivially satisfied. Therefore, we have to deal with only the first equation and with the theta double dot term dropped. We have only this equation. If I make this assumption that precessional angular velocity is much smaller than the spin angular velocity, this typically happens in a top, for example. The top is spinning at a very high rate, but its axis is precessing at a very low rate. And if you make that assumption, then we can drop all quadratics in or square terms in psi dot, and then I am left with this simplified form. So, I have contributions from this equal to m x. all quadratics in psi dot are dropped. And then I can obtain psi dot in terms of the applied moment and the spin and inertial properties of the body. For a spinning top, for example, the moment that is produced about the point O is due to the weight, and that is given by mg rg. I have marked out rg in this diagram. It is the vector OG essentially, and so essentially rg is the length of that vector OG, and its component, the moment arm, you see this length is rg, this length is rg, and the moment arm is this much, and this is theta, remember. Therefore, this moment produced by the weight is mgr sin theta, mgr sin theta, mgrg sin theta. Therefore, for a top, the precessional angular velocity can be determined in terms of its inertial properties, spin, and its location of the center of mass. You can obtain this approximate relation. Let us look at a simplified derivation right from the angular momentum calculation about O, and this we are going to use later on in problems. This is the net angular momentum about O. There is no approximation till now. If I say that it is a case of steady precession and the precessional angular velocity is negligible compared to the spin, then you will find that first of all steady precession means this goes off, theta dot is 0, theta is constant, and what I am going to do is I am going to drop out any contributions from psi. Therefore, I can write this simply as I p k cap. I am dropping out all these terms involving psi dot, considering that they are quite small. I am assuming that steady precession with very low precessional angular speed. Then my angular momentum just becomes, it is very simple, I p k cap. What it means geometrically, this also I should point out, is that the angular momentum, you see why do we have angular momentum? Because of the spin angular momentum and the precessional angular momentum and possibly also nutational angular momentum. Right now we are assuming steady precessions and no nutation. Therefore, the net angular momentum is a vector sum of these two, one is because of the spin, the other is because of the precession. The net angular momentum H O is the sum of angular momentum due to spin and angular momentum due to precession. If I say that the precession is very small, then the net angular momentum is actually in this direction along the axis of symmetry. This is roughly the picture that you should have. If H p is very small, the actual angular momentum will be almost coinciding with the axis of symmetry, not quite, but almost. And if I can say that okay, I will neglect the precessional angular momentum contribution, then the only thing that remains is along the axis of symmetry. So, that is the angular momentum. If I take the rate of change of angular momentum, because there is no local derivative, p is constant, I is constant, therefore, del t of h naught will be 0. What remains is the frame derivative term, which is omega f cross h naught, and that will give me I p omega f cross k cap, and omega f remember is this expression I have written in green. And if you take this cross product, and theta dot is of course 0, no nutation, and I am going to consider therefore this term only contributes, and that is how I get this expression. And this is same as what I have obtained here. Next we look at the second simplification, which is the torque free precession. In this case we have a body which is spinning, has been given a spin about its axis of symmetry, and it is now in space, or it is moving something like a frisbee or a disc which has been given a spin, and it has also been projected. So, it is in free motion. As it moves, it is a torque free precessional motion. In this case we will again consider that theta dot is 0, there is no nutation, and psi dot is constant. So, we are left with only one equation, and here even the moment about the x axis, that also goes to 0. So, on simplification I obtain this equation. What I can calculate from here is the precessional angular speed psi dot. Now, there can be two values. The spin is provided, to the body, and so that is a constant as we have assumed. I can calculate the precessional angular speed psi dot, which can be 0 or it can be this expression I about the axis of symmetry times spin angular speed divided by I naught minus I times cosine theta. Theta remember is this angle. It is the angle made by the axis of symmetry with the inertial direction. Theta is the angle made by the axis of symmetry which is now precessing, it is precessing, and the angle made by this precessing axis of symmetry and the vertical inertial direction, that is theta. And what does this equation tell us? That also we should note, since there is no moment whatsoever, therefore, angular momentum must be conserved. Okay, we can have two cases when there is precession. It may not precess also. If you can give a nice initial condition, then it will not precess. There is a solution with no precession, that means it is going to spin and move, but there can be precession if there is a misalignment with the angular with the angular momentum. If when it is released, there can be initial disturbances which can generate a initial precession, and that is going to remain like this. We can have two kinds of precession depending on the sign of I naught minus I. Remember, I naught is the moment of inertia about the two perpendicular axes perpendicular to the axis of symmetry, and I is the moment of inertia about the axis of symmetry. If I naught is greater than I, what we have is direct precession, what is known as direct precession. By direct precession, it is meant that the direction of precession is same as direction of spin. That means, if it is spinning like this, then the precession is also in the same direction, counterclockwise, as seen from the top. The other is retrograde precession. Sometimes direct precession is also called prograde precession. Prograde precession, and retrograde precession is just the opposite. When I naught is less than I, you will find that psi dot will be negative of the spin direction. That means, it is going to precess in the other direction. If this is the spin direction that I have already shown, then in case of retrograde precession, I have this will be the direction of precession. This is the moment of inertia tensor. Just to remind you, when you have a slender body like this, I is about the axis of symmetry, and that is quite low compared to the moment of inertia about the orthogonal directions to the axis of symmetry. Therefore, I naught is greater than I, and if this is the spin as shown, then the precessional angular velocity is in this direction as shown. You can imagine that there is a cone, a body cone, which is rolling on a fixed space cone. We have looked at this problem of rolling cones, one cone rolling over the other, and this is where you can picturize this system by considering these two cones. The body cone is fixed to the body, it is spinning, and it is rolling over the fixed space cone. That is why it is called space cone, it is fixed in space, and this body cone is fixed to the body. Therefore, the motion of this body can be thought of as a cone, a body cone rolling over a space cone. And remember that the net angular velocity of the body in such cases is along the line of contact of the body cone and the space cone. As you make the spin faster and faster, as you increase p, so that the primary contribution comes from the angular velocity or spin angular velocity, which means that the net angular momentum is almost aligned to the axis of symmetry. In that case, the body cone becomes very thin, and therefore, its precessional speed you can now calculate from here, from the rolling action of the body cone on the space cone. Now, this is the situation when you have direct precession or prograde precession, and the opposite thing happens in case of a body for which the moment of inertia about its axis of symmetry is greater than that in the perpendicular direction. Therefore, I naught, which is along the two axes perpendicular to the axis of symmetry, if that is lower than the moment of inertia about the axis of symmetry, then you have the retrograde precession, and in this case the two cones are like this. One cone, the space cone, is the interior cone and the body cone goes out, but the angular velocity vector is on the line of contact. This picture of this cone is just for visualization. Let us look at some problems. Two identical discs are rapidly rotating freely on a shaft with angular velocities equal in magnitude and opposite in direction as shown. The shaft in turn is caused to rotate slowly about the vertical axis in the sense indicated. It is rotating in this direction. determine whether the shaft bends as in A or as in B because of gyroscopic action. Because of gyroscopic action, whether the shaft have tendency to bend in as in A or as in B. This is a problem from the book of Merriam and Craig. I look at this disc separately, one of the discs separately. As I mentioned just now, that if the because this angular speed is very low, it is mentioned that it is slowly being rotated, whereas this is spinning rapidly. Therefore, the net angular momentum can be considered to be along the axis of the disc, though theoretically there will be a contribution from this rotation also to the angular momentum, but we are going to neglect that. Therefore, the net angular momentum about the center of mass of the disc can be considered to be along the shaft axis. If that is so, then the precessional angular velocity, which is same as the slow rotation, this generates a moment about the center of mass of the disc. This calculation we have seen for the spinning top or spinning axisymmetric body. This is the moment being generated, and I have drawn essentially a free body diagram. Therefore, on the shaft a negative moment must act. This is a reactive moment on the shaft, and this moment, how is it going to bend the shaft? This is a moment that is usually drawn like this. Moment vector I have drawn initially. This is the way the moment acts, this is the way the moment acts. Therefore, we have the case B. Therefore, the shaft has a tendency to bend as in B. Let us proceed to the next problem. A spinning projectile moving through the atmosphere with a velocity v as shown, which makes a small angle theta with its geometric axis, is subjected to a resultant aerodynamic force R acting opposite to v as shown. If R passes through C slightly ahead of the mass center G on the symmetry axis, determine the minimum spin velocity p for which the projectile is spin stabilized with d theta dt equal to 0. Take the moment of inertia about the symmetry axis as I naught and about the transverse axis as I. This is again a problem from the book of Merriam and Craig. First thing, we fix up the coordinate frame. Now, here this is axisymmetric body, I can fix up the coordinate frame as we have done. Before, you should note how we fix up the coordinate frame for axisymmetric bodies. The capital Z, so the x axis is defined as a cross of capital Z and small z. This is the way we defined, and that is perpendicular to the plane of the screen and into the plane of the screen, and y axis is shown, that completes the right handed coordinate system. Why this choice of frame is important? Because I am going to use the same equations as we had derived. This was the governing equation, we have derived it for the kind of frame we have discussed before, and that same kind of frame I have fixed for this body because I wanted to use this equation. Now, what is the moment here? Moment is because of the drag force R, aerodynamic drag force R, and that can be written as R bar is shown in the figure, times the drag force magnitude R times sine theta, that is the moment. We are considering that this is steady precession case, there is no nutation, theta is not changing. And then I get this quadratic equation in the precessional angular speed psi dot. For real solutions, that means if it is to have real precession, psi dot must be a real solution of this quadratic equation, and for real solutions I must have the discriminant greater than or equal to 0, and from there I get bounds on the spin angular velocity, the spin angular velocity. So, there must be a minimum spin angular velocity for this body to be spin stabilized. This is known as spin stabilization of a projectile, and this is typically used in bullets. For example, there is rifling in the barrel of the gun which gives a spin to the bullet or to the projectile, so that it does not deviate from its path due to aerodynamic effects. So, that completes our problem, and this lecture we have looked at gyroscopic forces on spinning axisymmetric bodies and discussed precession with and without external moment and looked at some problems. With that, I will close this lecture.